right, kids.
You know your topic.
We'll catch up a little bit more tomorrow on logistics. Listen to my goal for today. My goal for today should be, let's check the evens on section 10.4. However, I'm going to make that goal tomorrow. I'm going to meet that goal tomorrow instead of today. You guys are supposed to finish 10.4 over the break. A few of you might not have. Let's just put it that way. And my justification for not going over this homework. Oh, catch up. Come on. Come on, you're doing so well. Anyway, my goal for there we go. Not going over this homework today is that we did have one last example that we didn't get to finish on
That was why I couldn't do it.
We've been saved.
I didn't understand it. That's why I couldn't do it.
Yep, the very last one.
Absolutely.
Now, listen, a lot of you guys, before spring break, remember how we were doing spot checks like every day? And so you're kind of caught up on hopefully chapter 10 homework, if you were here. So, 10.4 is going to be due tomorrow, and then we only have one more section until our test on, let's see, hold on. One more section is today and tomorrow. We're going to get through half of it today and the rest of it tomorrow. We're going to have a full review day on Wednesday, and then the test will be on Thursday. Okay? So, the nice thing is, hopefully you're fairly caught up on homework tonight. You're just going to try and finish 10.4 if you have not yet. And if you have finished 10.4, you can start on 12.3. That's awkward. 12.3 from another book? How are you going to do homework from another book?
You posted it online.
No, I'm not.
Okay, I lied.
Although it will be online. But write down this example in your notes, section 10.4, and meanwhile, I'm going to pass out the homework from the other book. David, Jason, write the example.
Yes.
Correct.
Hey guys, might have just helped me out. We might have already finished this one, but we'll still not check 10.4. All of you guys is coming back from Lord. But I am going to do it really fast just so it's on the notes or it's in the notes online. And you guys can review. Okay, Perla. We got 6 the Thursday night before break. And then I went to Baja and I kind of started playing a little better. Not that one. Baja, California. This trip. And I was like, okay, I'm beating it. It's not this weird one that comes back again. And then it came back and it came back again. It's round 2. But from what I saw in kids that got this, after round 2, they were done. So I just need to make it through round 2. That probably sounds all like, and this year, I can't. Airplane mode right now. As in quad. Alright. You guys have this in your notes, so I should be able to go super, super, super fast. So we're just reviewing really quickly, and you guys are seeing if you understand what is there. We turned in corrections on Thursday, but a few of you might have remaining corrections to get turned in. So get that turned in by the end of the day on, what was it, Chapter 9A West?
Yes.
You probably should get back to Chapter 9B quizzes. I think they're graded, but I'll just give them back to you. Or did I already get them back to you? Okay, here we go. Hyperbola. Question, real quick, as I'm going. How are you supposed to know that this is a hyperbola to begin with?
It's a minus x squared.
It's a minus x squared. Good, good, good. What am I doing right now? Walk me through
Yeah, you grouping then completing the square.
grouping the y terms and the x terms. And what am I moving to the other side?
The 63. Or negative 63.
Oh, this is a degenerate, isn't it?
Yes.
Okay. Why am I factoring out a 16 but not a y?
Because
You need the y. You want
I need the y's in there to complete the square. So I only factor out a constant. I already factored out stuff from this one, so it's no big deal. Why am I putting 2 blanks on the other side also?
Because you need the balance.
I need to keep everything am I getting the 4 right here from?
Completing squares. You divide it.
Yeah. I take the middle term, I cut it in half, and I
Squares.
square it. Good. Take the middle term,
Cut it down. Square.
and then
Square.
why am I writing 64 and then minus 1?
Because
Because
there's a negative,
16
plug in
times
negative,
four.
and then
Good.
16 times 4 is.
Good. I need to see what the plus 4 meant. It was 16 times 4, and what the 1 meant. It was minus 1. Why was this degenerate? What ended up happening on the right-hand side?
Equals 0.
So even though it looks like a hyperbola, is it?
No.
No. It looks like a hyperbola. That's the best guess that you could have done straight from the equation. Best guess. But when you solve, as soon as you start to complete the square, as soon as you see the 0, you're like, ah, it's a degenerate. It's not a conic section. Well, degenerate one, which we say is not technically a conic section. But if we were to keep solving, which is what we did on Thursday, that keeps on throwing me off. X minus 1 squared. There we go. I think we ended up with 2 intersecting lines. Is that right, kiddos? 16, y plus 1.
Yeah.
Y plus 2. We moved this guy to the other side. We plus or minus square rooted everything. I think we divided by 16 somewhere in the process too. We ended up with y plus 2 equals square root of 16. X minus 1 y squared plus or minus. Nope, the squared is gone. Because you square rooted plus or minus and divided by the square root of 16 is 4. Good. And then we plus or minus 1/4. X minus 1, subtract 2. And if we wanted to graph those, we have a slope and we have a point that is technically point slope form. And I think this is where we ended truly with x being 1, y being negative 2. Putting our point having a slope of up 1/4-ish. Oh, I remember doing this, yeah. We're on the board or something. So we have 1 line. We go the other direction, up 1/4-ish, down 1 right 4-ish. Done, Dylan, done. So sadly, you did not get to see me find center vertices, foci, and equations of the asymptotes of a hyperbola. We didn't really review hyperbola, but we did review looking at a standard form equation seemingly of a conic, thinking about how it should be a hyperbola. We started going with completing the square, saw that it was degenerate, and solve. Thank you for letting me update my notes. Now my notes are good to go. I'm just happy we didn't grade our homework today. But please remember, hyperbolas were the main point of section 10.4, right? And you have centers, HK, you have vertices, which are the distance found by the denominator, the square root of the denominator of the positive term. If it's an x positive term, you're going horizontally to the vertices. If it's a y positive term, you're going vertically to the vertices, and to be one of those ones, one of these ones. The foci is a little bit outside. That's why the c squared formula is a squared plus b squared. C gets to the foci. And that's about it for hyperbolas. So tonight, if you have not yet, once again, finish up that homework. For tomorrow, we'll check it tomorrow. Go over questions tomorrow. What do you guys need to be studying and reviewing? Of what?
All of the
Section
different conic
10.1,
sections.
inclination. M equals tangent theta. Inclination. How to find the angle of inclination, how to use slope to find it. The only other formula in 10.1 I think is angle between. Tangent of theta equals absolute value of m2 minus m1. All over 1 plus m1 m2's. And your absolute value. 10.2, you have parabolas. Parabolas, you have something like y minus k squared equals 4p x minus h. Or, that's for y squared. That's for one of the weird right-left ones. Or, you could have an up-down one being x minus h squared equals 4p y minus k. You have a directrix, which is p the other direction from the focus. Is there anything else special about the parabola? Not really. The center is, or the vertex is HK. If you have positive, that's an up-down, you're going up. Negative, it's down. Positive, right, left, you're going right. Negative, you're going left. Then we had ellipses. y minus k squared all over b squared equals 1. If the x squared has the biggest number, then it's going to be a major axis that's horizontal. And then the y, the b is going to be the minor radius. You have the major radius, the minor radius. Center is hk. Foci are found by adding c to the x values if it's a horizontally oriented one. C squared equals a squared minus b squared. And the foci are found by adding c to the k values, the y values, if it's a vertically oriented one. And then we have hyperbolas, and those are the two formulas we just looked at. So the only thing I haven't, I think, reviewed is eccentricity of an ellipse. It's e equals c over a. And slopes of the asymptotes of hyperbolas. M equals plus or minus rise over run coefficient under the y squared term over the coefficient under the x squared term. That brings us to 12.3. Alright, this is the homework from the other book. As you can tell, if you look at it, there are only 2 pages of actual homework, and the only homework problems are the circled ones. I want you guys real quick on your handout to go to number 17 real quick. The submarine problem. This is the bonus for this homework. So go ahead and put little parentheses around the number 17. This is the bonus problem. Has to do with the bow of a submarine.
Is that the last section for chapter 10?
We're splitting chapter 10 up to be 10.1 to 10.4, and then this 12.3. That's 10A, that'll be a test. And then 10B will just be sections 10.6, 10.7, that'll be a little quiz, and then we're done with chapter 10. Because 10.6, 10.7 goes into kind of this whole other, it has some correspondence or some relationship with the beginning of chapter 10, but there's so much in chapter 10, it's just better split up. So number 17, put quick parentheses, what did you say?
I just put 12.3 under like chapter 10.
Yes, because it's not our chapter 12 at all. Our chapter 12 is very different. This is from an old book I used to use. We're skipping our 10.5, which is good and all. Some of you guys were asking, I think it was you, Tyler, or me, like an ellipse, what if you have it rotated? Like its major, minor isn't horizontal or vertical. What if it's diagonal? That's section 10.5, and it's a good section. But for calculus, I like ending conic sections with this instead, which is three-dimensional conics. Alright, so as you guys are in your notes, 12.3, there's going to be a 12.3a, that's today, and a 12.3b, that's tomorrow. It might be a little bit in between. But there are 2 big ideas in 12.3. The first one gets you from problems 1 through 10. The first one, 12.3a, gets you problems 1 through 10. And then 12.3b gets you to 11 and 13. So anybody notice what the second page was for? What is this? Yeah, answers to the odds. So I gave you a back of the book. Yeah, you know, I got you. Alright, you guys writing this down? I have something cool to illustrate this idea, but sadly I gave it to someone to see if they could fix it. And they're like, it's a challenge, I'm gonna get it done, and I never got it back. So
They stole it.
they did steal it. I'm gonna see if I can get it for you guys for tomorrow. Go ask Mr. Clinton. But right now my cool illustration is in pieces. It's not that cone thing. It's different. It's like a wire metal 2-dimensional representation of a hyperbola. And I have axes and I can spin it around and make it 3-dimensional, but that's I know I'm all out. All my sick people before then I was going to Baja and I got all distracted. So I didn't get to get to the store. Oh, I have napkins in that top one. Let's do that. I have napkins in that top cupboard where the on-roll sheets are. Yeah, you want to grab a pile, Jason? Okay, quadrant surfaces. Long story short, we're going 3D. Without classes. We're going 3D. Taking a two-dimensional conic section, which you guys have been dealing with. We're going to try to make it three-dimensional. And I want you guys to highlight how are we going to make it three-dimensional? By rotating. By rotating. The surface region is going to be similar to surface area, which I know you guys have seen since, I don't know what, math 6, math 7, the algebra, something like that. Surface area. You can think of that as like an outer shell. Surface region, just the outside, just the outer shell. Easter just happens to be those little plastic Easter eggs, and if you pop it open, surface area is kind of like the Easter egg itself. Whereas the solid region, that will be measured in volume. That's the use really messy. And that has to deal with the insides. And even Cadbury eggs while we're on the topic of Easter. You can think of the surface area as being the chocolate shell and the volume being the creamy inside. If it was full, I don't think it's actually full for a Cadbury. Anyway. I think of a Whopper, that might even be better. A Whopper, those little malt balls. You can think of surface area as being the chocolate shell and then the volume being the Whopper, like the malt on the inside. Anyway, we're done. You guys know what's going on. We have surface area, we have volume, we have a surface region, and a solid region. Paraboloid. Now, if you still have your homework paper out, let's see. Paraboloid. Number 1 is a paraboloid. Actually, number 1 and 2. Number 1 and 2 are paraboloids. Now, they give you an equation to make a parabola, and then you spin it, you rotate it. I'm going to go ahead and not give you an equation, not make you start from an equation today. I'm just going to give you a parabola, like a general one, just so we can get an idea of each of these figures, or each of these shapes. So let's just do like a basic parabola. And make it somewhat symmetric, like it's supposed to be. Now, parabolas usually go on forever, right? But to graph these, they're going to cut it off somewhere. Which, if you guys still have that homework sheet out, if you look at it, it's going to say something like from this point to that point. From this point to that point. This one, let's say I cut it off around x equals 2. And then if I spin that, that'll end up translating to also be x equals negative 2. I have to cut it somewhere just to make it like a finite figure. Otherwise, it'd be kind of complicated if it was infinite. So even though a parabola does go on forever, we're cutting it off. That's a two-dimensional parabola. Has no thickness, has no depth. To make a paraboloid, we have to rotate a two-dimensional parabola about, now we could rotate it about all sorts of different things. We could rotate it about the line x equals 2, it'd be kind of weird, but we could rotate it around y equals negative 4. In calculus, we'll rotate around all sorts of different things at the very, very end of the year, the last thing we do. But right now, we're specifically making a paraboloid, and the only way to make a paraboloid is just to rotate a parabola about its special axis of a parabola, the axis of symmetry. Special axis for a parabola, the axis of symmetry. And in this one, since I have an up-down parabola, its axis of symmetry is going to be the y-axis. Now I'm always going to show my rotation using this little curved arrow about the line I'm trying to rotate it around. And believe it or not, on a test, if I were to say, rotate it about this particular axis by you showing me this little curved arrow right here. By you showing me this little curved arrow, you get the point for saying, hey, you knew where the axis was and your idea was right. Whether or not you got it right or wrong, hopefully you got it right. But just by showing me this arrow, you're saying, hey, this is the axis of symmetry and I'm going to rotate it about. And I I know it's hard, but I need you guys to visualize something since my really cool demonstration is not in my room and it's in pieces somewhere. I want you guys to imagine that this is on a string. So the y-axis is a string. Okay? And then I have just this little parabola. Imagine it in wire and paper. And it's like glued to the string. Okay? If I were to start spinning that string, what would happen to that little wire frame of my parabola? It would come out, okay? It would come out, and it would be spinning whether you go this direction or whether you go the other direction. It would come out, and as I would go faster and faster and faster and faster, I could think about what shape am I generating, what shape am I showing, and the shape that you would be showing is the surface or the outside of a parabola. And how do we show that? On two-dimensional paper. We could be super snazzy and start making, we have an X and Y, and start making a Z axis. What are the dotted lines for? To show going back in, back behind the board, the solid line coming out from the board. We could go ahead and try to say, hey, the parabola is going to rotate, and as it rotates, you're going to have another portion to this parabola. But the long story short, you just need to show some sort of rotation going on. You won't be super snazzy, you can start showing some cross sections and make it solid on top. But if you're just trying to show this shell, I guess we wouldn't really show that solid part on top. If you want to be super snazzy in your pencil, you can do much better shading than I can up here in my smart notebook. You can actually say like, hey, look, there he is. And what's a paraboloid look like? Yeah, a little cup sort of. Top of the tulip? I don't know. An upside down bell? A paraboloid. And if you guys notice, the same way that my circle down here rotates, I just need to get this rotation in my figure, and I can get that rotation now. Guys, I went ahead and tried to show the XYZ axis just a little bit. But to be honest, it's not rocket science. You have a parabola and you say, sweet, let's spin it. It's good enough, I know what you mean. It's not gorgeous, but I got it. Does that make sense? And so you can see that rotation in the top. And you could do like what I did with my little, like, showing a different portion of my figure, and you can make it solid and have some fun with it. But you could just make a parabola and show a little spin on top and say, okay, there you go. But one more time. I want to see you choosing your axis of symmetry with this rotation arrow. That rotation arrow. And then I need to see some sort of spin in your parabola. Now, once again, in your homework, you're going to have to work with a specific parabola. They give you y equals x squared, so maybe you would plot the point 0, 0, 1, 1, 2, 4, actually plot a few points, and spin that particular parabola. But once you have your parabola, all you got to do to make your paraboloid is just to spin it in the correct direction. Now, what if we didn't start with parabolas, but instead we started with ellipses? We would make an ellipsoid. But the deal with ellipses, parabolas, we just spin them around their axis of symmetries in the sense of making a parabola and making that bell shape. But with ellipses, ellipses actually have two different axes, don't they? They have a major axis, and they have a minor axis. And this is just a little introduction to the idea that if you spin a certain figure around different axes, you're going to get different shapes. And once again, we're not going super crazy, and we're not rotating around some horizontal vertical lines outside of the shape. We're just going to stay within the shape, within the axes of the original shape. So we're going to start with an ellipse. Now, once again, in your homework, you're going to have to review how to graph an ellipse first, because like in number 4, 3 if I was to make you do it. And number 4, you're gonna have to get an ellipse first. You're gonna have to go back to the notes, section 10.3. How do I graph this ellipse? Divide both sides by 16, simplify. Find the center, find the major and minor radii, make my ellipse. You're gonna have to use your old information in your notes to get an ellipse. But for right now, just to get the idea down, let's go ahead and let's do a horizontally oriented ellipse. And let's make it go out, I don't know, let's make it go out 3 and up 1. Let's go out 3 and down 1. If you guys know much about sketching, you usually get a more accurate picture if you kind of use little loose lines instead of trying to make one perfect outline. Let's say that's a perfect ellipse. It's far from, but at least it's roughly accurate. I'm going to go ahead, since I'm getting ready for the next shape as well, I'm going to do the exact same thing and try to make it as accurate or as similar as possible. This one down here is going to be a little bit wider, so that's okay. And as I'm drawing this, guys, the major axis is going to be which axis? The x-axis, good. The horizontal axis going through the ellipse. The ellipse is translated to be whatever horizontal line would be in the middle. Okay, it's rough. So, if I say the very first thing for you guys to figure out is which axis I'm talking about and marking it with a green arrow, you guys just told me the horizontal axis is the major one. So since probably the ellipsoids rotate around the major axis, I'm going to show a rotation arrow around the x-axis for the first one. And the minor axis then is going to be the y-axis for the next one. Arrows. No. Okay. So if I'm asking you to spin around the major axis, I could also say around the line y equals 0. Show me that rotation, show me the line that you're spinning it around. When I said minor axis, same thing as x equals 0, spinning that around. And they're going to give you some sort of directions and homework as well, except in this one I think they actually just say the y-axis or the x-axis, and you have to figure out if it's major or minor and what shape you should be drawing. So once again, I want you to pretend the axis you're spinning it around is a string. And I want you to pretend that there is attached to that string a two-dimensional outline of an ellipse. And when we spin it, can anybody see the shape that it would make? I know I'm making you use your imagination, but what shape would that make?
It's like
Like a cucumber or a pill, maybe like, one of those Dacryl micro sort of things,
oh yeah.
right? Maybe like the body of a butterfly. It's going to be something thin. Now, how would we show that? I'll give you a way to remember it in just a second. But how would we show that? Well, just think we need to show that same rotation, that same going around rotation. Now, I know there are probably artists out there in this classroom that are going to do this much nicer than I will, but long story short, we just need to show the spin. You can show the spin in multiple places. Technically, if we were to do like the XY axis, we could kind of show this figure with what it would look like coming out. The problem, the reason why I don't do that, why instead I choose to use the same arrow is number one, it's easy to remember if I'm showing this rotation right here going around. I just need to show something of that same orientation on the inside. And if I were to show the other way, it would actually get confusing and start looking like the next one. Pencil, you can go into some shading and have some fun with it. But long story short, you can think of it as like a pill. You can think of it as like a Mike and Ike, sort of. just for sake of memorizing, here's my silly way of remembering it. Major, pro, that kind of goes together, right? I know if you're in the majors and if you're in the professional, I know it's a little different, but just go with me here. So we have the majors and we have the pro. If you want to think about it, it's kind of like a football. Yes, I know it's broken at the ends, but long story short, still kind of like a football. Close enough. So you can think pro, like you can think major, you can think football, or you think academic. Now, here's where it gets a little harder. When we come down to this other one and we have an oval ellipsoid going around the minor axis, I need you to think fan blade, or cheese wheel, or flat circular pillow, or
Baby bell cheese.
tire. Yeah, exactly. That's what I was thinking, like the little baby cheeses in the red packet for baby bells. Why am I saying that? If we were to use a z-axis, if we were to try to make our tick marks on our z-axis, we go out 1, go out 2, go out 3, go back 1, 2, 3. If we were to try to connect, this one, if we had this string right here and it was spinning in your hand, it would come out and whap it. Think of fan blade, right? Yeah, not that kind. So when you spin, this shape would come out and it would hit you. The other one stays pretty much self-contained. This one spins, but it spins very small in the sense of the distance it comes out because it stays just self-contained in that little pill. This one, the whole ellipse would come out and you would have this rotation. Now, if you wanted to, you could go ahead and try to have it be the other direction as well and show the third dimension because it's going to be spinning all the way around. And that might help some of you guys. I'm not going to make my axes, which means it'll probably turn out pretty badly. Once again, I'm not pretending to be an artist. But maybe some of you can kind of see that fan blade that I'm talking about. In the sense of that rotation that would be formed. So you think baby bell cheese, you can think, oh, that one was. You think a fan blade. And how many of you guys are like, I don't want to draw that? Okay, ready? You want to see my simplistic version?
Yes.
This one up here, my simplistic version would probably just be ellipse and then it'd be like, yay, it's a little one. Maybe you can at least do dotted. Makes it a little bit easier. This one, have your ellipse, and just be like, it comes out somehow, and it spins. There you go. Just make it fatter. It's not great. Looks kind of like a hairball. But anyway, whenever you have your ellipse, you're going to have it come out and be like, I don't know, but it's wide, and it comes out. You don't have to make it gorgeous, you don't have to make it pretty, you don't have to make it look like a fan blade or a baby bell cheese, but some of you are going to have fun making it look accurate, more accurate than I did, of course. But others of you, can't you see a difference between these two?
Yes.
Right? One's self-contained and the other one, it's not. Yeah.
Frisbee and one's like
So pro, major, football is on top. Bottom, minor, oblate, think obtuse, like an obtuse angle. It's a wider angle. It's going to be a wider shape. Goes around the little axis. Think cheese wheel, think flat pillow, think fan blade. I don't know. You guys see the difference, right? Even if it's not super gorgeous. What I need to see is this rotation. Okay. Now, hold on. So we've done parabolas and paraboloids. We've done ellipses rotated around the major and the minor axes, showing two totally different shapes, but still based on the same original figure. So what are we missing? Hyperbole. What do you need to divided by 4, the x you're doing it horizontally oriented, let's do it vertically oriented hyperbola.
It's gonna make an hourglass, but there's gonna be space in the middle.
Depending on which way you spin it. There's going to be the transverse axis and there's going to be the
It's gonna make a donut.
conjugate axis.
It's gonna be
Either a donut or an hourglass.
2 paraboloids or an hourglass. 2 bowls or an hourglass. I'm not going to make this one super particular in the sense of, if you guys notice, I'm not giving you equations for these, I'm just giving you the general hyperbola, that way you have an idea of what's going on. There'll be equations in the homework, so you're going to have to graph the original hyperbola first. I'll make them more narrow. So I'm helping you with the visualization right now in class. And then tonight you're going to try and put it together tonight and tomorrow night. Well, tomorrow night, remember we're going to learn how to do 11 and 13 tomorrow in class. You might want to work on 1 and 10 tonight. Not 1 through 10, but the circled ones that are there. Okay, do you guys remember which axis the transverse axis? Oh, never mind, hold on, pause. And get a hyperbola down the bottom one also. Try and get one that's pretty similar in size and shape. Trying to show you yet again one figure rotated about different axes can show or can generate different three-dimensional objects. This is kind of pertinent to today. Some of you have heard of 3D printing, right? In order to use a 3D printer, you have to somehow define the parameters. Now, the programming does help you in the sense that you can input a sketch. Well, they're super expensive, so we won't see one of those for a long time. But maybe at your colleges, universities, you'll see them. They're super cool. But you have to somehow give it parameters in order to have the printer generate the 3D object. If you guys haven't seen 3D printers, look it up. They're really awesome. When used for good. Anyway, transverse axes. Yeah, the most common objection is you can make a gun that is undetectable with metal.
You can only fire it a few times before it melts.
Transverse axis is the one that goes through, if you guys remember from hyperbolas. We're going to use this one. In this case, it'll be the y-axis. The transverse is the axis that cuts through. Remember, once again, when we put the rotation arrow, makes a difference. And then, maybe if you guys can imagine spinning, this one is going to generate two, in a sense, kind of self-contained bowls. Or you can think about it as 2 paraboloids. It's like you're rotating around 2 separate axes of symmetry. So it's kind of like you have 2 separate bowls, is one way of thinking about it. You have 2 separate paraboloids. You can try to make the different, you can make it 3-dimensional, no, sorry, you can make it solid by doing the cross sections. But long story short, 2 sheet. Hopefully this kind of makes sense. 2 sheet in the sense of you have 2 separate figures. And if you were to try to make this, you would need 2 different pieces of material, one way of remembering it. What's going to be different if we rotate it on the conjugate axis? Conjugate axis is the one that goes through, is parallel. In a sense, it does not intersect. And Tyler was saying earlier an hourglass, and this is, I think, what he was visualizing. In that, if you go about the conjugate axis, they're going to run into each other and form one solid shape. If you guys notice, that shape looks an awful lot like an hourglass, a wheel, rim. Not sure exactly what you want to compare. But you can think one sheet. Just make one piece of material. Alright, we'll get finished up 10 for tonight. Maybe start with saying 1 through 10, not all of them must be in the circle once. You have to learn or remember how to graph the tonic first, and then one extra step. One extra step. Okay.
Same as Derek.
Thanks, you guys too. Hang in there. I know it's a hard one.